D. Wilson Memorial Lecture. Stan Wilson passed away on November 17, 1985, approximately 3.5 years ago. Because we at Shannon and Wilson have had the dual privilege of being close associates of one of the recognized leaders in the geotechnical engineering profession, as well as members of the firm which he co-founded, we believe it to be especially appropriate that we establish a fitting memorial in his honor. This lecture is the first annual lecture in honor of Stan Wilson. The second lecture next year will be held in the St. Louis area in the vicinity of our Midwestern Regional Office. Many of you have received an announcement or seen an announcement of this first lecture containing a brief summary of Stan Wilson's professional accomplishments. We're not here today to eulogize this man, but to recognize and honor him in his professional accomplishments. In this regard, I would like to add a few biographical comments which were not contained in that announcement. Stan Wilson was born in Sacramento on a chicken ranch. He hasn't spoken much of his early years to his associates, but after completing high school, he worked for the State of California Division of Highways for about 8 years before returning to college to the University of Minnesota, where he left in 1943. And then he joined the U.S. Army Corps of Engineers. That assignment had a dramatic impact on his life. During this 3-year period of service, he was assigned to a short study program in soil engineering with Arthur Casagrande at Harvard University. He made such an impression on the master that he was invited back to Harvard to do graduate work when he left the Army in 1946. He worked half-time for 2 years and earned a Master of Science degree in 1948. His supervisor at that time, sitting right here, Bill Shannon, his future partner. Stan built the first model of the highly successful and well-known slope indicator at the Harvard Soil Mechanics Laboratory during the summer of 1948. He joined the staff at Harvard with Harry Seed in 1948, and he taught there until 1953 when the trustees decided to close down the soil mechanics program at Harvard University. He then joined Bill Shannon here in Seattle, where they established the firm of Shannon and Wilson in Ballard in 1954. Stan Wilson received virtually every honor our profession has to offer. The Huber Research Prize of ASCE, the Wellington Prize of ASCE, the Rickey Medal from ASCE, the Carl Terzaghi Award of ASCE, election to the National Academy of Engineering, and his final honor was the election to honorary membership of ASCE, which is an honor reserved for a relatively small number of active members. In 1964, he was designated Engineer of the Year by the Consulting Engineers Council of Washington. He was also the 6th Carl Terzaghi Lecturer, and he presented the Kirsten Lecture at the University of Minnesota. He maintained an active, continuing relationship with the academic world, lecturing frequently at the University of California, the University of Illinois, and also at many other universities. He taught special courses for the U.S. Army Corps of Engineers and frequently participated in technical meetings of the ASCE and the International Society of Soil Mechanics and Foundation Engineer, for which he was a special reporter in 1969 at the International Conference in Mexico City. He was a frequent contributor to the literature of geotechnical engineering, authoring over 60 professional papers on a wide variety of subjects. Although he was involved in the solution of many landslide problems and foundation engineering projects in the Puget Sound area and throughout the western United States, Stan Wilson was an internationally recognized authority on earth and rockfill dams, and he served as a consultant on many major hydroelectric projects throughout the world. These many and varied activities established him as one of the leading geotechnical engineers in the world. While Stan's innate ability to size up an engineering problem and rapidly come to a practical solution were his trademarks, his many other talents included mastery of virtually all of the building trades and machine tool crafts. Of course, many of you who knew him personally knew that to be true. He could fix anything from suitcase locks to watches to plumbing and any electrical problems. This ability led him into the design and fabrication of much of the original laboratory and field testing equipment used by Shannon and Wilson, and the initial development of the geotechnical instrumentation firm, the Slope Indicator Company, which he also co-founded. Stan was a real human being. He loved people and especially children. He was always made it a point when he was in town to come to company picnics, Christmas parties, and he entered into them. It was not just a passive thing with him. He was a devoted husband, father, grandfather. He had a great appreciation for music. He was a regular supporter and season ticket holder to the Seattle Symphony, in which his son Scott, right down here in front, has been a French horn player for, I believe, 18 years, Scott, something like that. We're pleased that Scott and Christine, Jeannie, are here. Would you please stand and be recognized at this time? Chris drove here from Utah to be here today. Scott came from Malaysia. His family is still over there. He was over there on a special time this past year, and we were very pleased that they could be here. It's our hope that this Stanley D. Wilson Memorial Lecture Series will foster and help maintain the thoughtful and practical approach to solving engineering problems which Stan Wilson epitomized. Now I would like to introduce our first Stanley D. Wilson Memorial Lecture at this time. It is a real honor and a personal pleasure for me to introduce Dr. Ralph Peck. I'm aware that there are many of you in this audience, particularly the geotechnical engineers, but many others as well, for whom Dr. Peck needs no introduction. Some of us have had the privilege of sitting in his classroom as students. More of you have worked with him on projects and sought his counsel. And of course, many more have studied his professional papers and his textbooks. Those of you who have received the announcement of this lecture have no doubt read a brief summary of Dr. Peck's professional life. Again, I would like to make some additional comments to expand on this information. The professional career of Ralph Peck spans a period of more than 50 years, during which time geotechnical engineering developed from a young discipline, practiced and dominated by a few, to one of the major areas within civil engineering, taught as an integral part of civil engineering curricula throughout the world, and recognized as an essential element of the investigation and design of almost all major civil engineering works. More than any other individual, Ralph Peck has served as a guide and leader in the maturing of this discipline. His impact on the profession has been most significant because of his commitment to education in both his academic and professional life. His teaching and research in the 32 years at the University of Illinois were directed toward integrating the theory and practice of geotechnical engineering. He believed that the complex process of evaluating problems and reaching decisions on difficult engineering projects could be taught. And he used effective methods for transmitting perspective and judgment, as well as the theory on which it was based. In this regard, his former graduate students remember well his course on case histories as a highlight of their education. I believe it was called CE 374 when I went through that particular activity. The students literally became a part of the consulting team with Professor Peck in the classroom on active consulting assignments. They tried their approaches and developed conclusions from information elicited from Professor Peck as the project unfolded. Their ideas were eventually compared with those actually developed on the project. Most of those students will not soon forget the initial trauma of stating the problem and summarizing their conclusions in grammatically correct English on one side of a single 8.5-inch by 11-inch sheet of paper. I think it might be appropriate to have those who have gone through that particular class to stand at this time. I see there are several here. Rad Squire is over here. Sally. Dr. Peck, there are quite a few of those in the audience. Would you all stand again? He was... Thank you. The outline of his 1973 presidential address to the International Society of Soil Mechanics and Foundation Engineering in Moscow provides some insight into his perspective. You should listen to each one of these. I think there is a lot of insight for us to think about. 1, the most fruitful research grows out of practical problems. 2, geology should be used to greater advantage. 3, our practice falls short of our knowledge. 4, simple calculations based on a range of variables are better than elaborate ones based on limited input. 5, construction deserves more attention in design. 6, instrumentation is no substitute for adequate design. 7, we should write with more discrimination. Lastly, our profession has a challenging future. That's good news. Ralph Peck's honors are many. He is an honorary member of the American Society of Civil Engineers, in which he has also served in several official capacities through the years. He is also an honorary member of the Mexican, Southeast Asian, and Japanese Societies of Soil Mechanics. From 1969 to 1973, he was president of the International Society of Soil Mechanics and Foundation Engineering. He is a fellow of the Geological Society of America and a member of numerous other professional societies, including the Canadian Geotechnical Society. He was a recipient of the 1974 National Medal of Science, awarded by President Ford. He is a member of the National Academy of Engineering and a fellow of the American Academy of Arts and Sciences. His other awards from the American Society of Civil Engineers include the Norman Medal, the Wellington Prize, the Carl Terzaghi Award, and selection in 1975 as one of the top U.S. construction men of the past 50 years. Most recently, he received the ASCE President's Award. He received the Washington Award of the Western Society of Engineers, the Moles Award in 1973, the Golden Beaver Award, and other honors and awards include the Outstanding Civilian Service Medal of the Department of the Army, Corps of Engineers in 1973. The record of Dr. Peck's honors and professional leadership positions provides only partial evidence of the esteem with which he is held in the engineering profession. His advice has been sought on many national and international geotechnical engineering projects. Among the larger projects with which he has had direct involvement are studies of foundations and stability conditions of ore docks around the Great Lakes and other heavily loaded structures for heavy industry, overwater runway extensions at LaGuardia Airport, the Trans-Alaska Pipeline, bridges and railroads and highways throughout the United States. He conducted the initial geotechnical studies for Chicago's O'Hare Field. Ralph Peck has held key roles in investigations and engineering of major tunnels, including the Mount Baker Ridge Vehicular Tunnel here in Seattle, which we're anxiously awaiting for its opening. Subway tunnels in Chicago, San Francisco, Washington, D.C., Baltimore, Los Angeles, and Dallas. He was also a key consultant to the development of the cylinder pile retaining wall system for I-5 through downtown Seattle in the early 1960s. Among his most challenging tasks has been that of specialist consultant or member of the board of major water impoundment and hydropower projects, including the Peace River and Mica projects in British Columbia, the Churchill Falls project in Labrador, the James Bay project in Quebec, where I believe he's going this weekend for some additional work, the Balfour County Pump Storage Project in Virginia, and a number of dams for the U.S. Bureau of Reclamation and the U.S. Army Corps of Engineers. He has served on major advisory boards for the Office of the Chief of Engineers, U.S. Army, as well as many of the Corps divisions and districts, the Savannah River Project, Cape Kennedy Saturn Causeway, and numerous other special defense projects. He was a member of the independent panel to determine the cause of the Teton Dam failure. Through his writings, lectures, and personal contacts, he has been a teacher of the engineering profession. It can truly be said that his overall philosophy of applying the observational method to the geotechnical branch of civil engineering made him a teacher of virtually all others who are already distinguished in this field. Please welcome with me our guest lecturer for the first annual Stanley D. Wilson Memorial Lecture, Dr. Ralph Peck. His announced subject is Learning from the Ground, Use and Misuse of Observational Data. Dr. Peck.
Thank you, Ray. I selected the title Learning from the Ground because to me it epitomizes the way Stan Wilson approached his jobs. He approached them without any preconceptions. When he was investigating something that had gone wrong, he did it by personal inquiries, by inspecting the job, by making observations. And as we have heard, he devised many of the instruments and procedures by which to make those observations. And having allowed the ground to speak for itself, he was able very often to arrive at a solution. Not that he could not use theory, he did often. But he possessed, in a very high degree, a fundamental knowledge, a strong fundamental knowledge of the physics and mechanics of his profession. This morning at breakfast, something occurred to me that I hadn't thought of for years on this latter point. I decided it was something I should relate to you. He came to Illinois to give some lectures. We were sitting around my office in midday, getting ready for his afternoon lectures. He was planning to leave that evening to take the evening train up to Chicago and the midnight train up to Minneapolis and St. Paul, where he was going to investigate a bridge foundation failure for the Minnesota Division of Highways. He was also that next day going to take an examination for a professional engineer license in Minnesota. It was his understanding that it was going to be an oral examination based on his experience. Sometime during the day, he got a telephone call, perhaps from Bill, I'm not quite sure, with the unwelcome news that it wasn't going to be an oral examination, it was going to be an all-day written examination. This was a bit of a blow to him, I must say, and I think for a few moments he thought of the possibility of heading back to Seattle instead of going up to St. Paul, but then he decided, well, there was really nothing to lose and maybe something to gain. But he had no reference books with him. It was one of these open book type of professional engineer exams. So he searched our shelves in our various offices, picked up some books with which he was familiar, where he knew what he could find, picked up a few handbooks, stuffed his briefcase with them, presumably read them on the way all night, perhaps, up to St. Paul, took the examination, passed it with flying colors. I don't think many of us could have done that. I'm pretty sure I couldn't without some kind of advanced preparation, real study time. I think his ability to rely on the basics of a problem, to sort them out, probably was what carried him through that day. I want today to take you through three case histories, if you wish, about learning from the ground. The first one is a very old one, in which the ground spoke for itself. The second one is a more recent one, in which the ground again spoke for itself, but nobody was listening. And the third one, which has to do with a dam that can be judged safe only on the basis of field observations, a job with which Stan and I were associated and on which we worked just a few weeks before he passed away. The first job takes us back about 50 years. And if we can have the house light dimmed, we'll see if all this sophisticated gadgetry will work. This is the construction of a subway tunnel in Chicago 50 years ago. You can see that the excavation procedure was labor-intensive. It simply consisted of slicing away the clay, throwing it by hand out to muck cars out in the end of the tunnel, and having it hauled away through the airlocks because the tunnels were built under compressed air. Experiment a little about the focusing here. And the procedure was rather elementary. The most advanced excavation was up in the top heading, where there was a miner and a mucker helping him. The miner would simply slice off slabs of clay, throw it down to the muck car, hit it almost every time. And as the excavation advanced, steel ribs, liner plates, were put up against the crown, against the soil, held in place by these posts, which themselves were supported by bearing blocks on another block of soil. You can see that was a pretty temporary support because the next group of miners were taking away this intermediate bench. In order to support that crown until the ribs could be extended on the intermediate bench, you see some little kicker blocks up there just to hold the lower end of the ribs. The next operation was to cut a slot on the side of the intermediate drift, put in some more footing blocks, and underpin the rib by another section of rib. While all this was going on, the fellows on the lower bench were excavating the clay away, putting up the liner plates, and underpinning the piece of rib that was next exposed by them. So it was a continuing process of advance, of support of the clay, and of transferring that support from the upper part of the tunnel down to the invert level. Up in that crown heading, this is a little closer picture of what's going on. This is in a different contract with a slightly different arrangement, but a very similar procedure. And you can see, I think, that the supports, example, for the crown heading are themselves a bit precarious. They're resting on blocks of clay with an unconfined compressive strength that at the most is probably half a ton per square foot. In other words, not very strong material. So even the foot blocks for those posts.
Thank you.
Even the foot blocks for those posts were by no means unyielding. And I think you can appreciate that every step of this operation lost a little ground. As every time the load was transferred to a new block, there was a little give. So there was movement going on all the time. Now, Chicago had had tunnels constructed before. The sanitary district of Chicago had built some large sewers, not quite this large, but this technique had been developed over a number of years. Everybody knew that when you excavated a tunnel, there was subsidence at the surface, and quite often damage to nearby structures. So everybody knew that tunneling led to subsidence. But that was about the only mental connection that was made. Nobody tried to associate, or perhaps if they were contractors even wanted to associate, specific construction procedures in the tunnel with specific amounts of settlement on the street surface. So there was no real understanding of what caused the settlement, other than the flat statement that when you dig a tunnel, it was inevitable that you got settlement. This is a little sketch of the principal excavating tool, the clay knife that you saw the fellows using up in the crown drift, for example. In soft clay, you could drag this through the clay with two hands, get a chunk that might weigh 60 or 80 pounds, and your helper would catch it as you sliced it off and throw it down. This is a diagram of the procedure I've just described, and I simply want to show the more specific kinds of support that you saw at each of the different levels. And point out also that after this lower face was excavated, which you saw, the last thing to go out was the so-called invert section to make the excavation complete. As you know, Dr. Tritsagi was the consultant to the city of Chicago on the subway tunnels. And we had set up a soil testing subsection, so-called. And indeed, our first duties were soil testing. When he got the job as a consultant, construction was just getting underway. And when we organized the soil testing laboratory, there were as yet no test borings that you would call at all modern test borings along the line of the subway routes. And so for the first few months, we were very much occupied in making borings and making laboratory tests to determine primarily the strength of the borings and to try to get ahead of construction with the boring program. But after a little while, just a few weeks actually, we were beginning to catch up, and we discussed, Dr. Terzaghi particularly, discussed the reasons why settlements were occurring and what might possibly be done about it. And he suggested it would be a good idea if we could measure some movements in the tunnel, see how much the ground was coming in. And with that suggestion, hardly saying more than that, he headed back to Cambridge and left us with a job to do. This is the gang that we had to do the job. The chief engineer of the subway had taken quite a fancy to Dr. Terzaghi and his new soil mechanics. And when any young fellow would show up for a job, if he had a master's degree in something or other in civil engineering, or if by chance he had taken a course in soil mechanics, because a few people had in those days, he'd say, send him off to the soil testing section. So we had a group of a few fellows, all of whom I think have turned out to be reasonably well known in their profession. Some of you will recognize some of them. Mike Salgo, for instance, who was treasurer of ASCE for a good many years. Chet Cease, who was head of the Department of Civil Engineering at Illinois after Professor Newmark, for example. I usually look like the rest of these guys. I think I had to go to the head office that day, so I wore some fancy clothes. But this group of us decided we would make measurements in the tunnel, see what we could get for Dr. Terzaghi over about a 72-hour period, continuously. We'd see what's going on. There were enough of us, so 2 at a time, we could be in the tunnel and observe everything that we could. The next slide that I show you is one that you can't read, and I know that it's very bad form to show something that you can't read. I will show you pieces of this that I hope you can read a little bit later, but this gives you an idea of the scope of what was done. Up at the top, across the top, you see a series of curves. They are settlements measured on the street over the tunnel at 20-foot intervals. It's 20 feet from here to here, for example. Settlement reference points at the building line, at the curb line, and 2 streetcar tracks. Those settlements were read every 2 hours through the roughly 72-hour period that we carried out these observations. Inside the tunnel, the heading was being excavated in a number of blocks: crown drift, intermediate, lower drift, invert. And the progress is shown by this intermediate diagram. When the start of the observations occurred, the headings were located as indicated by these heavy lines. As the crown drift started from about here, the intermediate drift from about here, lower drift from here, and so on. Each of the different colors you see up there represents an 8-hour advance. So that in the 8 hours, from the time we started until the next 8 hours, that sort of pinkish block of materials came out at the locations indicated by the numbers keyed over here. As soon as we had the possibility to put some reference points in the clay either side of the tunnel and could measure across, we began to measure the distance between those reference points to see if they came closer together. And those distances are plotted down here. We'll see them again a little closer up. Again, they're color-coded in with the times of excavation according to these 8-hour blocks. So that on this diagram, the results of the settlement observations, the inward movements from the sides, and the detailed excavation progress can all be related. We did a few other things. We drove ahead of the tunnel, as indicated over here on the left, some so-called spearheads, in such a way that we could measure out to the tail of them as we drove them, get a distance measured back to a fixed point, and then as the excavation came up to the location of the spearhead, We began to look for it, to feel for it, hope the miners wouldn't hit it before we found it, and make another measurement back to the reference point to get some idea of how much the clay out in front of the tunnel was moving toward the tunnel as we excavated toward it. We measured the settlement of the foot blocks after they were established. We established points in the crown and took level observations to see how much those points came down from the time the crown was first exposed until the 72-hour period was over. Now we look at some of the individual pieces of this diagram. Up here you see a longitudinal section just to show diagrammatically where we put the spearheads. For example, you can see that number S1 and 2. Those are spearheads that were driven ahead of the face. We couldn't get them in awfully far, but we could see how much that point moved in toward the tunnel from the front as we took away that 6 or 8 feet of material that you see. You see where that was located and planned by S1 and 2 in this cross section. You can also see in the cross section the locations of the cross tunnel lines. You also notice there, this is the spearhead, just to show how it was done. It's a little thing like this, an inch, 18 inches long, driven in by a pipe driving on these shoulders. While the pipe still had it in the ground, we could stick a rod in, find the location of the back end, get a good measurement to a fixed point. Take the rod, take the pipe out, of course, and then travel along, hoping you can see that open hole until you encounter the spearhead again. Here is a portion of the diagram showing something about the settlements. You can see the progress chart a little better, and you can see a couple of the settlement diagrams over the tunnel. Without going into the details of what we learned, I can simply point this out, that when the excavation started in the crown heading, with the crown tunnel going in this direction, and you started at this point, you see very little pink, just a little touch of it on the left-hand end of that upper diagram. That means that hardly any settlement had occurred when the heading had reached this point before we started our observation. And very little settlement occurred while this material was taking out. That's the pink zone up there on the very left-hand edge. Already that told us something we didn't know, that in this particular tunnel at least, removing that crown heading itself didn't cause much settlement out ahead of the tunnel. That had been just a source of argument up to that point. Now we knew it wasn't happening. You can see that when this next section was taken out, that is when the crown heading went from here to here and the intermediate went from here to here, that fairly large bluish section represented the settlement that took place. You can see that was substantial. And you can see the settlement was still going on, the next sort of pink section, when the whole tunnel went by. And you could also see that quite a bit of settlement was still going on, the last colored section on the right there, when this invert block was taken out. So we're beginning to be able to relate what was going on the street surface with the excavation sequence itself. I'd also point out here that these were the locations of the cross-tunnel lines. We started out with some before excavation started, so obviously there'd been some movement here before we get them in. Then when we went by this location, we established another one. When we went by this location, we established some more and followed the inward movement of those points. And here we have the results of that exercise. You'll recognize that same diagram up there representing progress. And here, with the same color keys, we have time, reading downward, and inward movement. This represents 1 inch. So you can see that there was more than 1 inch of inward movement at most of these reference points. That is, that's the total diameter decrease, the sum of the inward movement of the 2 points. Now, when Dr. Terzaghi came on his next trip, we brought this diagram out and showed it to him. he concealed his pleasure with some difficulty. He really was quite excited about it. He didn't want to overdo any praise. We thought we'd done a pretty good job, and we realized that he thought we had too. But the thing I remember most about his looking at it, he said, you look at these points. Why did you draw a smooth curve through all those points that aren't anywhere near the line you draw? I said, well, our observations aren't any better than that. We do very well if we can be right within 1/4 of an inch. And he said, you can measure a line 20 feet long more accurately than 1/4 of an inch, I'm sure. Yes, but remember, first of all, we're targets down there. The miners enjoy seeing how often they can hit our tape, throw these clay chunks. All sorts of activity down there. They don't stop mining just because we're there. It's pretty hard to do. That's really the accuracy we have, so I just drew a general curve through them. Quite obviously, he didn't believe me at all. But he didn't press the point, since I seemed to be a little argumentative about it. And he said, well, we shall see. Keep that in mind, because it turned out to be an important thing in my life. Here's a little bit more of the observation. We kept track of the air pressure. You notice, again, time is reading down, that at the end of about the middle of the second day, contractor let the air pressure drop a bit. That did have some effect on what we observed. And a few days later, we came in to make some further measurements of crown settlement. These are curves of settlement point up in the crown. You can see there's a little kind of a kick in it. Again, I drew curves generally through the general direction of the points, but not following the points exactly. Also, would like you to notice the date. These observations were made between May 9th and 12th, 1932. Today is the 11th of May. 1932, 1939. Today's the 11th of May, so I can almost guarantee you that exactly 50 years ago this hour, probably I, and certainly some of my buddies on the soil mechanics gang, were in the tunnel making these measurements. So this is sort of an anniversary. We made some other squeeze tests in other tunnels with similar results, although the results varied because the contractors used somewhat different mining procedures and the tunnels were somewhat different configuration. And I'll show you a couple of those a little later. But that was in May, you recall, 1939. In September, we got a long report from Dr. Terzaghi. Memorandum concerning results of squeeze observations on the Chicago subway project, in which he discussed the settlement observations which were being collected religiously over all the tunnels, and these squeeze tests. And here he has replotted those movement curves that I drew the smooth curves through. You'll recall that I had, with his change scale, what looked like a parabola going down through here, and a similar curve coming through here, and so on, ignoring these little bumps. Terzaghi in his report said, well, now the progress through the 20-odd feet that you observed in this squeeze test was pretty regular. The beginning of the 26th of April, the tunnel was at about station 164 plus 16. As it advanced through the day, got up to this station, 164 plus 21. It got there by about half a day, and rate slowed down a little bit, but this is a pretty smooth curve. So progress went along smoothly. You'll notice that the bump, this hump that comes after the trough in all these curves, kind of line up at the same time. He said, now you would expect in a plastic material, really plastic material, like the clay we normally see down in the tunnel, that things would happen gradually and that there would be a successive movement as each of these curves that look sort of the same, but the bumps would follow along at time intervals corresponding to the rate of advance. But he said that doesn't seem to be the case. They all happen about the same time. I've always suspicioned, he said, that these plastic clays really behave like brittle materials. We never get to see them in that state because by the time we see the clay, they've experienced enough deformation to have become plastic. But this rather demonstrates how rather brittle the material was as the tunnel went by. Furthermore, he said, there was something he noticed. These curves all had the bumps. And in addition, particularly on some of the other squeeze tests that I'll show you a couple in a minute, the crown reference points didn't come down smoothly either. They would often settle a bit, then they'd turn around and perhaps go up, and then come down again. So I said, this is all part of a reasonable pattern. So look at that top diagram up there. He said that rectangle represents the place where the future tunnel goes. And I'll draw a rectangle just to make it easy to describe. And the crown is represented by that upper rectangle. That drift goes ahead first. And when it goes ahead, the crown begins to come down. The roof sags, in other words. And you get that lowermost curve, which is labeled E1, if you can read it. The sides haven't come in much yet because the side hasn't been excavated that far yet. So those sidewalls stay about where they were. Then the whole tunnel advances, and the sidewalls being high compared to the width of the tunnel, the sidewalls begin to move in a little bit, move in very energetically, as a matter of fact, and as they squeeze in, that has a tendency to push the crown up. So we should expect to see a reversal in the direction of the crown, or at least a slowing down of the movement. And then as we go on a little bit farther, the general movements resume again, the crown comes down again, the sidewalls come in again. So it's natural. It makes sense that these inward movements show a reversal of trend, and it's similarly natural that the crown tends to show a reversal of movement. When I was writing the final report of the subsection's work on the subway, I reproduced this squeeze test on contract S5 on one 8.5 by 11 sheet, eliminating much of what you saw. And here now are the diagrams representing the shortening of the cross-tunnel lines. And you can see this time I learned my lesson. I didn't try to draw smooth curves through these lines. These represent the actual readings. And if we look at some of the other tests, here's one on the twin tube that went alongside the first one where we ran the test. You can see the crown settlement, for example. The crown came down a ways, then it kicked up a little bit, and then it started coming down again. The side movements were irregular, but rather similar to what we had before. And on still another contract, in appreciably stiffer clay, you see what happened to the crown? The crown came down and went right back up where it came from. There the crown came down and went back up where it came from. Presumably if we'd had to observe a little longer, they would have again started to show downward movement. But that reversal of movement in the crown was really there. Much less movement in the sidewalls, but again, the same sort of reversals. Much less total settlement, because it was a tighter mining job, rather different procedure. But it illustrated that Terzaghi was right about these movements meaning something. So we learned two things from these sets of observations. Nothing to do with any theory, unless you want to call that little rectangle that Terzaghi discussed as representing theory. We began to learn where the settlements were coming from. That is, what construction operations led to what settlements. At first, the contractors were not at all happy to have us interfering with their work. At first, they regarded us as being spies, I would say, giving the resident engineer some sort of a handle to make life uncomfortable for the contractors. But as the contractors began to appreciate that indeed there was a relationship between damage that they might be causing and how they excavated. They got interested in preventing the damage. And before long, our lab group was getting a bit overwhelmed by requests for squeeze tests. The contractor would come to us and say, I'm getting more settlement as I approach this building than I have been getting before. What am I doing wrong? What's going wrong? Can you come in and run a squeeze test and find out? And we began to do that to the considerable advantage, I think, of the properties around the subway. We also pretty soon began to teach the contractors how to run their own squeeze tests, because after all, it was a fairly unsophisticated operation. So we learned quite a bit about cause and effect, simply by letting the ground speak for itself. The other lesson I learned was the one Terzaghi taught about those curves. And that was, don't throw away the results of a field observation just because it doesn't fit your preconceived notion. How often do we see that? How often do we see the results, say, of some piezometer readings and something goes a little wild, apparently? See observations we don't believe. Very quickly say, well, that's an instrument error. Something's wrong with the instrument. I have gradually over the years come to the conclusion that that's the last thing that's probably wrong. Granted, instruments do go wrong, and you have to be conscious of that possibility, but before you decide that the instruments are giving faulty indications, better believe that they're right, because they're trying to tell us something. Maybe something we don't know, maybe something we don't want to know. But they're trying to tell us what the ground is doing. We better think that they're right until we're absolutely sure they must be wrong. And that little exercise with Terzaghi of some 50 years ago was a lesson that I hope I haven't forgotten yet. It certainly comes to mind rather frequently. This is obviously a different job. This is a nuclear power plant. In the background, you can see the two containment vessels with the reactors in them, and around it, the various auxiliary buildings. The scheme of construction here was to excavate a big hole down to rock through 40, 50, even 60 feet of overburden, which consisted primarily of glacial lacustrine clays with some sand seams and sand beds in. Establish the reactors, reactor foundations on the bedrock, and then backfill the hole with engineered fill. As the backfill came up to the level where there would be the foundation for a structure, or whether there would be some conduits or something of that sort, when they got to that level, you'd build those foundations and then keep coming up with the backfill. This structure is a very stiff, heavily reinforced concrete building. It rests on continuous footings at about twice the depth that you see exposed here. Those footings were placed on a mud slab that was cast on the fill as the fill came up to the appropriate elevation. As the fill came on up and reached yard level, people began to notice that there were some openings between the mud slab and the reinforced concrete strip footings that rested on them. Those footings were already supporting very stiff vertical walls. And it appeared that somehow in some locations the mud slab was settling away from the rest of the footing. This, of course, led to an investigation. And it turned out that something had gone wrong with the fill. It didn't have the degree of compaction that it was designed to have. Why that's so is not part of this story. The part of the story that interests me, at least now, is the fix and what the ground was trying to tell us. There were several options for taking care of this problem. One would have been to dig all the fill out again and start over. That would have taken quite a lot of time, and time at that stage of construction was supposed to be worth money. Another would have been to underpin this structure and some of the others that might be in the same situation. That would be expensive. For this building, a third option, which I think Skip Hendren was the first to suggest, was that we fill the building up with sand and put sand around the area to surcharge the area. We were able to compute that you could get enough sand in this configuration that you see to increase the vertical stresses in the soil at all depths beneath the structure in the fill to values greater than the stress would be under the building during operation. And we reasoned that if we placed this surcharge and waited until the fill was consolidated, until the primary consolidation was over, we would have a satisfactory foundation. One of the merits of this procedure was that it would permit a quite reliable forecast, we thought, of the settlement that might be expected during the lifetime of the structure. And that was a very important consideration to the NRC, who, of course, were looking over our shoulder in connection with the project. What we reasoned was that if we took settlement observations as the fill was being placed and thereafter, we should get some primary settlement. If we would make a plot of the settlement versus the logarithm of time, we should expect to get the characteristic time settlement curve that should merge into an inclined straight portion representing secondary consolidation. And when that portion was reached, we could say we've accomplished our purpose in consolidating the soil everywhere to stresses greater than structural experience in the future. Furthermore, if we would leave the load on long enough to establish the trend of that curve, we could extrapolate it to 100 years or 50 years or whatever the lifetime was that somebody would choose to consider. And that should be a conservative estimate of what the ultimate settlement would be. Because that would be what the settlement would be of this structure if we left the fill in place. Of course, we're going to take the fill out and put a load back on that probably wasn't going to be quite as much as the fill, and therefore the real settlement should be less than what we would obtain by assuming that the fill was there all the time. So that was done. The fill was placed, and here is a representative log time settlement curve for a point in the building. And you will recognize that you see this first part, which certainly looks like primary consolidation. You'll see a second part that defines a pretty good straight line, and that straight line lasted for about 100 days. This would be day 200 here, at which time the structure was unloaded and rebounded a bit, and after rebounding began a settlement which was more or less parallel to a little bit flatter slope than the one that you would extrapolate from that loaded area. So with considerable confidence we could feel that if you're talking about 30 or 50 years, you go out here 30 or 50 years and you can read off how much the settlement should not exceed. We felt that this was a foolproof way of getting at the maximum settlement. Now there is some scatter, as you can see. We recognize this as being associated with the optical levels we were taking, and somewhere along in this period we established some deep reference points with Boros anchors at various depths so that we could measure the settlements with a micrometer gauge instead of by optical leveling. And when we did that, we got points that defined this straight line with virtually no scatter. Same straight line we have here, but a more refined and more elegant set of data. So we felt quite confident about this. You will also notice that this curve, and incidentally I didn't draw this curve, I copied this from one of the engineers had done, it does have points that don't quite fall on that curve. Once again, the actual data have been ignored a little bit. People say, well, that's very close to a primary settlement curve, but it really has a few variations. Well, part of the story, of course, was these settlement observations. But another part of the story was the installation of piezometers at various depths so that you could observe the excess pore pressures associated with the fill and see how it dissipated. And one of the interesting things would be whether the time required for dissipation of the excess pore pressures corresponded to the time to reach somewhere near 100% consolidation. To investigate that, I made these plots, now with an arithmetic time scale, not a logarithmic scale, and plotting the settlement up there in the top as a function of time instead of log of time. All of a sudden you discover that there are two increments of settlement. There's that settlement that took place mostly in the latter part of February, and then it slowed down, almost stopped. And then there's another settlement that took place between March and April, and then it more or less stopped. And this fit pretty well with such history as we had about the way that surcharge was placed. It was placed generally in two increments. People didn't keep exact track of what fill was where on what dates, so that surcharge line is somewhat idealized. But nevertheless, one batch of fill went on, about half of it, in the period up to the end of February. Then there was a wait for about half a month, and then the rest of the fill was put on. And you can see that the settlement up there corresponds pretty well with the placement of the surcharge. Surcharge went on at a gradually increasing rate. Settlement began to pick up. Settlement continued a little while after the surcharge had become constant, tapered off. Then the new surcharge was placed, and the same thing happened again. So it looked as if we had two episodes of settlement, two episodes of primary settlement, if you wish. What were the piezometers doing at this time? They looked something like this. There was a bump, followed by another bump, and then not much happened for a while until the load came off. Now, the piezometers didn't go up very much. As you can see, this is something like 3 feet or so, and this is perhaps 5 feet from here to here. The total surcharge is about 20 feet of earth, which should have been something like 30 feet, say, of piezometric pressure. So everybody was a little surprised, including myself, that these peaks weren't higher. And there was an argument with our friends at the NRC who said, theoretically, those peaks should show 15 or 20 at least feet of rise when you put that fill on. And if they don't show that, there must be something wrong with the observations. On the other hand, it seemed much more reasonable to me, at least, to say that the ground was actually considerably more pervious than we realized it was. We knew it had sand pockets incorporated in it and so on. It must have a better drainage system than we thought inside. And the pressures were dissipating almost as fast as we could put the load on. And you could almost read that up in the settlement curves. So that instead of peaking way up, the pressures were dissipating to such an extent that we got rather small humps. And the pressures dissipated quickly after the loading stopped. Then came another batch of load. Instead of going up another 10 or 15 or 20 feet, as you would expect at 100% pore pressure, they only went up something like 25 or 30% pore pressure and then dissipated rather rapidly. To me, that looked like a good sign. The ground was more pervious than we thought, that we were getting our consolidation even more rapidly than we had a right to expect. The argument didn't seem to fly with the NRC, who said, well, we think, since it's clay, the pore pressures should be higher than that. Therefore, maybe the piezometers aren't below the water table. Maybe they aren't saturated, something of that sort. Well, you may have noticed in the photograph I showed that in the forefront of the picture was a pond. It's a cooling pond that had been excavated for cooling water for the plant. very close to the plant, and we recognized that the piezometers might be below water table, so we said, well, let's raise the pond level about as high as we can get it, as quickly as we can. Unfortunately, we couldn't raise the pond and get that all over with and have the water tables established before we had to start putting the fill on. So there's a certain amount of confusion as to how much of this rise in pond level might be associated with rise in piezometric level. But we were successful in flooding all the piezometers except the uppermost ones. The uppermost ones did the same thing as the lower ones. So as far as we could see, all the piezometers were below the water table, and there's no reason to think that they shouldn't have worked on that account. Indeed, the pond followed this dash curve, and you can see that the pore pressures, once they dissipated from the surcharge load, followed more or less reasonably the behavior of the pond. Finally, when the surcharge was taken off, the pore pressures went down and came up a little bit. Now, at another point, this latter phenomenon was even better accentuated. You'll notice this dip in the piezometric curves. We had probably 50 piezometric observations of this type around the plant, and many of them showed that as the surcharge was taken off, the pore pressures went down, then bounced back again, and dissipated. That's what they should do on relief of load. When you take off X feet of head, if you had 100% pore pressure response, you should get, from briefly, X feet of decrease in pore pressure level. We discovered that they could only take these readings at intervals. This wasn't an automatic, every 10-second readout automated procedure as we might have today. And every time we didn't get one of these dips in some piezometric observation, it was because observations weren't made at exactly the time when that fill was taken off. Whenever an observation was made at the time when the fill was taken off, close enough to that time, we got this little dip, which gave considerable confidence, I think, to the idea that the piezometers were doing what they should, and they were simply telling us that the pore pressures never got very large, which means that the foundation was fairly permeable, which means that we had achieved our consolidation even more rapidly than we had hoped. If we look at this piezometric curve, we can recognize the same thing, not quite as big a hump on the first loading, pretty good-sized hump under the second loading. There are dozens of these curves. They all show these characteristics. My interpretation of this was that the ground had spoken. The ground had told us that we had succeeded in consolidating the material to a point where we had achieved 100% consolidation under loads at least as high as those that would exist in the future, and therefore our prediction of settlement on the basis of the extrapolation of the secondary curve was a conservative and a reasonable one. And here's where things sort of fell apart. The NRC said, no, you haven't done this correctly. What you should have done, and what we insist you do now, is take undisturbed samples, run consolidation tests, determine the pre-consolidation load from the consolidation tests, and show us that every place you have exceeded a pressure that will be reached at these given points by the structure under its operating loads. It's obvious that that experiment was doomed to failure in the first place and statistical misinterpretation in the second. Because if we had developed pre-consolidation loads in these materials, as we undoubtedly did under the surcharge loading, sampling would do nothing to those values except lower them, as you all well know. So that when we tested those samples, we would get pre-consolidation loads in the samples smaller than the real ones. That was a strike against us, you might say. Secondly, there are certainly many statistical variations in this material. There are hard spots and soft spots. Some materials got better compacted than others. And statistically, we were going to get samples of some of the softer zones as well as the harder zones. So even if the average pre-consolidation pressure might turn out to be as great as that underneath the actual structure in operation, there are bound to be some values that are lower than that. My feeling was that the structure is already taking care of that. If there are stiff zones in the soil and the load is going through those stiff zones, the structure has told us that. It's gone on the settlement curve showing us what the settlement behavior is. There's no reason why the arching that takes place over a soft zone shouldn't continue to take place over a soft zone, so that's not going to affect the trend of the curve in the future. But you can see that the routine of sampling, testing, leads to conclusions that are at variance with what the ground was trying to tell us in the full scale in the field. Now, if we did not have this full-scale test, we only had the possibility of doing sampling and testing, that's what, of course, we would have to do. We would have to make our best guess as to what the pre-consolidation loads were and what the settlements would be on the basis of the samples we got. There would be statistical scatter, and we'd have to decide what kind of an average we wanted to take and how good we thought that average was. And if we were approaching the job initially from that point of view and had made a settlement calculation on the basis of such tests, we would have been delighted if somebody would come along and say, let's make a full-scale test and see how it checks out. But we didn't do it in that order. We made the full-scale test first. The boring, sampling, testing routine, which is a sort of a syndrome that we get into sometimes, was bound to lead to the wrong answer, did lead to the wrong answer, or at least it led to an answer for which there could be misinterpretations or differences in interpretation. And so here is, I think, a misuse of the procedure of letting the ground tell us what's going on. This ground was telling us, as best it could, what was going to happen under this building in the future. The ground was really speaking to us, but the right people weren't listening. And that is a misuse of the observational procedure. This last example is Gardner Dam up in Saskatchewan on the South Saskatchewan River. It's a project that was in the planning stages, design stages, beginning back in the 1940s. Bob Peterson, who was a soils engineer for the Prairie Farm Rehabilitation Authority, the PFRA of Canada, had been a student of Arthur Casagrande's, went to the job, set up a good Harvard-type lab, the latest equipment as per the 1940s, began to make stability calculations for the dam and to design the dam. It's obvious that this is in landslide country. This is downstream of the existing dam, slump topography all along. It's up in the Bear Paw Shale region. The dam indeed rests on the snakebite member of the Bear Paw Shale, which is the most bentonitic of all the members of the Bear Paw Shale. Everybody recognized this was a very tricky foundation, to say the least. Bob Peterson arranged for Arthur Casagrande to be a consultant on the job. Arthur realized that it was a difficult job. He involved Terzaghi, so they both worked on it for some time. After working on it for a few years, Stan Wilson came to Harvard. And I'm sure somewhere in that time he became acquainted with the job. He probably had something to do with the instrumentation and with the tests on the materials. Now the dam itself turned out ultimately to have very flat slopes. you're looking at a dam. We're on the crest. The toe of the dam is way out here. Flattest piece of country around is the dam itself. Here we are again up there. This is dam all the way. There's the powerhouse way down there. You can see the landslide topography around it and the failed slopes and this virtually flat ground. In the bear paw, in the snakebite member, there are benedict seams. And along many of those seams, there had been movements of geological origin associated with the valley cutting by the river and so on. So there are many surfaces in there that are old slip surfaces. One of the first things Arthur Casagrande did when he got associated with the job was to say, well, let's forget stability calculations on the basis of soil tests and calculation in theory. Let's go back and back analyze some of the existing slopes that have failed and some that haven't failed and see what we can learn. Here's a chronology that goes far beyond those times of various analytical stages in the design and a lifetime of that dam. Starting in '43, when Bob Peterson made his first tests, according to lab tests, he could use two different sets of parameters. These were undrained parameters at the time, cohesion of 15 psi and a friction of 10 degrees, apparent friction, or just plain 20 degrees, 20 psi cohesion and no friction. Then came the back analysis of the slopes. And my goodness, that turned out to be a cohesion of 3 psi and only 3 degrees. Came 1961, Boulder Shear Conference in 1960. Effective stresses now made their way to the United States. And we find effective cohesion 0 and effective friction angles back figured to be somewhere between 5, 7, or 9 degrees, depending on the history of the slide. Came 1964, Skempton's-Rankin lecture, and we learned about residual strength. And people realized these are old slip surfaces, therefore we should be using residual strengths. So some tests on residual strengths of different kinds of equipment. 0 residual cohesion, of course. Low values, the highest you could get about 4.5, the lowest about 2. And to come up to practically the present time, 1979, after the dam has been in existence, and we have a history of behavior, and we know that the factor of safety, as you'll see shortly, has got to be pretty close to 1. People tried to make more analysis to see if they could get 1 as a computed factor of safety. And it turns out that to get a factor of safety of 1 back figured from the existing behavior of the dam, and assuming the factor of safety is 1, you have no effective cohesion, and the friction, residual friction angle is something in the order of 2 degrees. That's quite a history of design, spanning virtually the whole history of shear strength in soil mechanics. Well, this is the section of the main part of the dam. Couldn't get it all in one diagram. Starts out at fairly modest slopes, 4 to 1, flatter 8 to 1, and so forth. The original dam stopped up here above the pointer. After a redesign, they flattened the slopes so the toe came out about here. And the final design, the slopes keep on going out there. This slope, average slope, is 85 to 1. Now that could be a little misleading because they carried it out to this point because there had been some wrinkles in the ground at this point, and they wanted to be sure that they put surcharge over the zone where they knew the failure reached. And they also knew that the failure was occurring along a slip surface in the shale somewhere above a sand layer incidentally, which was drained very effectively by wells. Now there's hardly any dam that I know of that is more instrumented or better instrumented, better observed than Gardner Dam. Here are slope indicators all over the place. These are the ones that existed as the time of this drawing. A great many of the slope indicators sheared off and had to be replaced. These are just the ones that were working at any one time. There are piezometers along the surface of sliding. above the surface of sliding and so on. So that today we know without much doubt what the pore pressures are, even on the surface of sliding, and we know what the movements are, where those surfaces of sliding are. Here's a bit of the history of construction. Starting in 1964, the filling began, and the fill is represented by that brown shaded line. See, the fill was completed in about the fall of 1966. And by 1966 fall, when the fill was completed, there were downstream movements at some of the slope indicators of this much. Now that is something like 4 feet. As a matter of fact, there was very serious doubt whether they could get the last increment of fill to top the dam out without having a failure, a real failure going downstream. Fill movements were accelerating, as you can see, quite rapidly in the latter part of 1965. But they persevered, they flattened slopes, and they did get the dam topped out. The water came up, as you can see by the bluish line. Water came up a little slower than the fill, but they were accumulating water behind it as they were constructing. And after that, movements continued, and for the next number of years, as shown by this slide, the reservoir fluctuated between about the same limits each year, a few lower and a few higher years. But the dam was still moving downstream along the surface of sliding. That shearing was occurring. And these curves were not getting horizontal. They were flattening out a little. But the real question, as of, say, 1978, was, are these movements going to approach a constant rate of movement? Will it still keep creeping along, in which case there was a possibility that sometime it might decide, having passed over sort of a peak, to increase? That would be dangerous. Or is it going to taper off and slow down? Looking in a little more detail at what happens with the reservoir movements in the last years of filling, you can see the reservoir up above, fluctuating up and down. You can see, for example, in 1977, that the reservoir didn't get as full. That was a drought year. The other 3 years, it reached its peak. You can see in the next pair of curves for different parts of the dam that each year, when the reservoir was filled, there was a jump in movement. And now we're talking about smaller movements. These are still meters, so we're talking about a few centimeters now. But each year they flattened off but didn't quite get horizontal. The next year, another bump. This year, with the fairly small loading, we still had curves that were showing continued movement even under the relatively low movement. So the question has persisted on that dam for a long time. Is it indeed going sometime or other to decide to accelerate and take off? I want to point out that it is possible to make some pretty elaborate and realistic, in a sense, stability calculations. The red line is the known location of the shear zone. There are slope indicators going through it, and they have displaced, there's no question where that shear zone is. Piezometers, you can see a few of those black dots. They're above, below, and in the shear zone. You can see the piezometric levels near the shear zone, especially here in the most active part. They're higher than the surface of the dam, and they haven't dissipated very much, just very slightly in the lifetime of the dam. Since we know where the shear zone goes, a stability analysis can be made in which the boundary conditions are pretty well fixed. And here is the latest of the stability analyses that the PFRA carried out a few years ago. Breakout just down below the end of that 85-to-1 slope. Shear surface, which is the bulk of the resistance, very well known. We don't know exactly where the upper surface is, that is where the active zone ends. So they took 3 different positions and made a calculation accordingly. Piezometric pressures along those back slopes do not vary appreciably with reservoir level. Piezometric pressures along the shear zone also don't vary much with the reservoir level. So the result looks something like this. If you assume the shear strength of, say, 9 degrees residual strength, and the 3 different possible positions for the active zone, you get 3 points with the minimum, and you see a factor of safety of about 1.7. Well, the movement behavior you observe certainly isn't compatible with a factor of safety of 1.7. You'd say it's closer to 1. If you repeat with other values of friction, you get different values. When you get down to 2 degrees, you discover that, yes, you can get a factor of safety of 1, and that's where that 2-degree figure came from that I mentioned to you. And here is a relation that they developed between friction angle and factor of safety. So you might say that after 20 years of development in shear strength, after 20 years of collecting information, after 20 years of trying to make stability analyses, they finally achieved success. We can now get a factor of safety of 1 for something we know is on the verge of moving, if not actually moving. And that looks realistic. But still, it isn't really realistic, because you'll notice that all 3 of those surfaces of sliding emerge into the pond at different reservoir levels. When you make the calculations, you discover that the reservoir level shouldn't affect the factor of safety really at all. The measured pore pressures along those back surfaces are pretty much the same for various reservoir levels. They're all below the lowest reservoir level. But we know that every time the reservoir goes up, the movements get a kick. So even this calculation doesn't tell the whole story. How is one to judge the stability of Gardner Dam? Certainly not by stability calculation. So we've taken 20 years for the calculations to roughly catch up with reality. PFRA, quite rightly, under the guidance of its various consultants, and somewhere back here 10 or 15 years or so, Stan Wilson became a member of the board of consultants that reviews these things. PFRA people began to plot the downstream movement per year against the years. And they drew this band and saw that indeed the movements are decreasing, that the displacements seem to be flattening out. But again, that nagging question, they're not horizontal yet. And these are hard to define. They also decided that there was a relationship between what they called the reservoir thrust and the amount of movement. As they took as a base level the lowest position of the reservoir where it intersects the slope, and calculated the total lateral load on the dam due to the water above that level. Because certainly the rate of movement ought to have something to do with that lateral load. And these numbers represent that reservoir thrust above elevation 541. You can see that when the reservoir thrust is low, the rate of movement is lower. When the reservoir thrust is high, the rate is higher. But there's a lot of scatter even in as late as 1978 or 79. So that's not very comforting. It doesn't still quite answer the question. About 6 years ago, after Wendell Johnson retired, or died actually, and was no longer in the board, I was appointed to take his place. So Stan and I and the former chief engineer of the dam became the board of consultants to look at the present history of the dam. And I first made my acquaintance with Gardner Dam. We had a meeting, and Stan was not altogether satisfied with this. It didn't really answer the question. We had an all-day discussion with data, and near the end of the day, Stan said to the PFRA people, "I'd like you to give me the numbers, give me your data on reservoir thrust, give me the elevations of the water level at the beginning and at the end, at least the lowest and the peak values for every year. In fact, give me all the readings. I'd like to take him home and work with them. So they obliged him. And we went to the hotel, had a dinner, and Stan went to his room. I had a couple of ideas I wanted to work on. I gave up with mine about 10 o'clock. They weren't working out. Next morning, 7 o'clock, Stan and I met for breakfast. And Stan was very excited. He said, I can't wait to show you what I've got. He says, I think I really understand what's going on. I plotted this stuff up, and it really looks like something. And this is his plot. All of the preceding studies had talked only about the maximum reservoir thrust each year. It occurred to Stan that the minimum value had something to do with it too. He said, if I plotted these values like you would plot a consolidation test, for example, you have starting up there at the top a certain settlement in 1969, a certain downward movement in this case. And then came an unloading period, and unloaded, not all the way back, but unloaded back to that point on the left. And the next year, another load came on, and the reservoir thrust went up to this value, and the corresponding movement could be plotted. He said, I didn't worry about rebounding occurring because it didn't look like these points were backing up, so I just ignored that, and every time I simply drew a horizontal line from the settlement that occurred in one year and started with the load at the subsequent year. He said, this is what you get. Now, you must ignore these last 2 points because Stan's worksheet actually stopped here. I added a couple of these later. He said, look at those. Every one of those curves is a little flatter than the one before. That means the ground is improving. If those were parallel to each other or if they were getting steeper, that would be a sign of weakening. But that's not happening. They're getting successively flatter. And that means the dam is getting safer and stronger, albeit rather gradually. Stan could hardly wait to get to the office that day and give a little lecture to the powers that be about how he got this and some other calculations that he made with it. I had always, in the last few years, come to think of this as Stan at its best, because I don't know anybody who got more pleasure out of working with good data, these were good data, than he did. And he worked with it with imagination and could see things that hadn't turned up because other people hadn't played with things to that extent or with that much intuition. So that was an exciting morning. It was a time I remember very much. It was the last time I saw Stan. Stan, you must realize, was younger than I by all of 6 weeks. I used to kid him about his being the junior. But we were pretty much twins chronologically, at least. And we talked about a lot of things at that Gardner Dam meeting at breakfast and dinner, other than the behavior of Gardner Dam. We talked about the future, and I remember Stan saying 2 things. One was, I don't want to spend the rest of my life around old people. He says, I'd rather be with young people. And he said, I don't want to get old and decrepit. I want to go out with my boots on. Well, the following week, after this meeting, Stan was looking forward to going to Detroit, where he got his honorary membership in ASCE, something that he prized very highly, and where he got the Rickey Medal. And then the next trip he took was to Africa, where he met the fateful mosquito. And I can't help but thinking that Stan got his wishes. He went out a little sooner than we would wish him to have gone, certainly. But he certainly went out with his boots on, and I suppose in the long run, nobody can wish for more than that. Thank you.
Thank you, Dr. Peck. That was truly informative, inspiring. And I think that we can all say that throughout this lecture, he has performed his usual task of trying to get one idea across to us. And I think he has succeeded in that. There may be some questions that some of you have been generated by this lecture, and Dr. Peck has consented to respond to those, should you care to direct them to him. Are there any questions at this time? Doug? Excuse me, did you hear the question? The question was, in hindsight, would it have been possible to assume that they would have been working with this week of material?
Can I answer that? Yes and no. I think at a very early stage in the conception of the dam, people realized this was going to be an unprecedented job, and that it would be a very difficult job. People were, I think, surprised at the extent of the movements. I should point out that Gardner Dam and Oahe Dam on the Missouri River were essentially contemporaries. The Corps of Engineers were meeting many of the same problems at Oahe as were going on up there, and these folks were talking to each other. So I think they felt that while they might have troubles getting the dam completed, if they got it to crest elevation, the odds were very good it would stay there, and it should start improving. The budget, of course, for the dam was exceeded several-fold, and perhaps if people had known how much the excess would be, they might not have undertaken the project. On the other hand, the province of Saskatchewan depends mightily on the irrigation from this project, and the people now realize and strongly believe that they very much need the dam. So maybe the problems that weren't foreseen have turned out to be an ultimate good. But to answer your question directly, I think people knew it was a very difficult problem. Both Arthur and Carl said it was one of the most difficult jobs they were ever associated with, that they were at the edge of knowledge. They probably didn't know how long they were going to stay at the edge of knowledge.
Is there another question?
Definitely. The Lower Baker slide did catch us by surprise. I think that's fair to say, that the group there was Stan and Bill Swigert and myself. We would not have been surprised if that thing had gone off in the wet season. In fact, we were surprised that it didn't. We really thought we had some breathing room to fix things up when it got dry. And we were surprised to find that that wasn't so. So the ground told us some things. It didn't tell us quite all that we would have liked to have known. It didn't tell us because we hadn't had the opportunity to observe, really, that in a dry spell, when cracks develop and so forth from shrinkage, a little bit of rain will go a long way and kick it off. So the next time we have a Lower Baker, we'll probably be a little more suspicious. But this is once where we were misled by what we thought the ground was telling us. We weren't around long enough to get the whole story from the ground. So I would have to say, yes, there are times when the observational procedure can easily mislead us. Sometimes we don't have time enough to wait to see what it all adds up to. Of the times that I can think of, though, I think it's fair to say that that slide was probably the most surprising surprise that has happened to me. And I think maybe Stan and Bill would have the same thoughts about it.
Dick?
Have there been any unusual surprises on what you observed at the Mount Baker?
Question was, were there any unusual surprises at the Mount Baker Ridge Tunnel project?
I think in general the answer is no. The observations in connection with that first lower drift indicated bigger movements than we had thought should exist. That wasn't necessarily a surprise. It was an unpleasant development, let's say, but it happened at a time when it was a good time to do something about it on the very first drifts. And so steps were taken that were effective after a couple more drifts. From then on, the settlements were within the limits that seemed reasonable. So there, I think it wasn't so much a surprise as that we found out with the first observations that we had to tighten things up, and having done that, it worked. Incidentally, Dick, I should have commented that those clay knives are a far cry from certain TBMs that you see these days.
Does anyone else have a question? Everybody satisfied with what they have heard and ready to apply it? I would like, again, to express our appreciation to Dr. Peck for taking the time to bring these thoughts to us, to come here, prepare it, present them to us. And I'd like just now to invite Bill Shannon up here, the former supervisor of Dr. Pecks at Harvard, and ask him to make a special presentation. Bill, would you do that at this time?
Ralph, I take exception to being your supervisor, believe me. It's my very great pleasure, Ralph, to have a little presentation for you, and if you'll come up here, we'll see if we can find it. Shannon and Wilson had a plaque constructed. Oh, there, you hold that. There you go. And it is a presentation to Ralph Peck in grateful appreciation for the first Stanley D. Wilson Memorial Lecture. And we hope you can find some place in your cubbyhole somewhere to hang that.
Thank you, Bill. I'll certainly make one.
Well, I want to add that I'm glad you're listening to the ground, Ralph. There you go.
Thank you, Bill. We're told that we are to vacate this room by 6 o'clock, which is about 15 minutes from now. I think the university has another activity scheduled here. And we would at this time invite you all to the second floor. You can take a stairway at either end, or I believe there's an elevator out here if you want to take the elevator, up to the Walker Ames room, which is upstairs on the south side of the hallway. I think it'll be evident. And enjoy a time of light refreshments, and you can take time to greet greet Dr. Peck, also members of the Wilson family, and of course speak to anyone else that you care to speak to. We thank you all for coming today and taking part in this occasion. And with these remarks, we are dismissed. Thank you very much.